So, hello everybody, my name's Tom. Sorry I'm starting a bit late, I was having a good chat at the front. Right then, so today we're going to talk about blazing fast PromQL. This is a project that I've been working on now for about a year or so. And yeah, hopefully take, how long do we have, do you know? Half an hour? 35, okay, good. With questions, nice, thank you. So yeah, take half an hour to explain what we've done here. So a bit of an introduction. As I said, my name's Tom. I'm really honored to be basically giving one of the first track talks at KubeCon. This means that all of my Anchorman memes are going to be nice and fresh. I think in 3 days' time you're going to be really sick of Anchorman quotes. But yeah, I work for a company called Grafana Labs. Who here uses Grafana? Wow, excellent. Yep, I'm technically the VP product, but I'm actually just a software engineer, by trade at least, although I don't do many PRs anymore. I started the Cortex project. Cortex is one of these CNCF projects to do a horizontally scalable Prometheus. I also started something called Wilkie about a year ago. We announced it at KubeCon. I was invited to be a Prometheus maintainer about 2.5, 3 years ago as well, which is pretty cool. If you want me on Twitter or on GitHub, there you go, and that is not my photo. So this talk is not about Cortex, but I just want to give a brief intro because it'll be relevant to the rest of the discussion. So Cortex is this CNCF project. We started it 3 years ago, and it's to build a horizontally scalable kind of clustered Prometheus. So we do high availability, we do replication, we do all of these kind of things. And really, Cortex is about giving you, solving some key problems with Prometheus. So if you have multiple independent Kubernetes clusters, and you run independent Prometheus in them, you want to have a global view of all your metrics, that's when you might consider using Cortex. I think the audio's cutting out. Is it okay? Yeah, okay, we'll carry on. Yeah, you could also use other projects, like Thanos exists, solves very similar problems. There's an excellent talk by Bartek in the audience here, and myself from PromCon 2 weeks ago, where we kind of compared the two systems. But they're set out to solve the same problem. We also, in Prometheus, if you guys use Prometheus, who uses Prometheus here? Hopefully everyone, right? Otherwise, why are you in this talk? But if you've experienced, sometimes, you might need to upgrade your Prometheus server, you're going to end up with gaps in your graphs from that restart. Maybe you need to upgrade the host it's running on or something like that. So this is another thing we try and solve with Cortex. We can do, HA deduping. Again, look at this PromCon talk. But the reason I want to talk about Cortex, and I want to put this talk in context, get those two words correct, is that in a Cortex cluster, in a Prometheus cluster, we have this kind of rule, you should never really query more than about 100,000 time series in a single query. And this is, you might hear people talk about cardinality, and this is kind of what they mean. Don't query too many time series, otherwise your queries will be slow. But when you've got a Cortex cluster, and you've got maybe 15 Kubernetes clusters all sending data into one Cortex instance, you're going to have 15 times as many time series per query as you will in Prometheus. So it's very easy to get yourself into a very high cardinality situation with Cortex. And this is just something, something that happens naturally when you start using, when you start aggregating together multiple Prometheus worth of metrics. And so it's not enough for us to say, don't do that. We have to actually come up with solutions for people who do that, because they do it all the time. And that's really where this talk comes from. When running Cortex, you end up querying millions of metrics normally. And you have to therefore do something about that. So yeah, the rest of the talk isn't really about Cortex. I'm sorry about that. If you're here to hear about Cortex, I understand the next talk in room 15 is about Cortex. But yeah, I'm going to move on now. So what we do to execute these queries, we actually just use the upstream Prometheus query engine, the PromQL query engine. And we actually, in Cortex, use the same storage format. And this is, I think if you're familiar with Thanos, if you're familiar with other Prometheus-compatible systems, this is really common. It's really easy to vendor and really easy to reuse this Prometheus query engine. So we just do that. But one thing you should know about the Prometheus query engine is it's effectively single-threaded. So for a single request, it's going to execute on a single core. It's going to aggregate together all that data, decode it, aggregate it, do whatever maths you're doing, all on a single core. And for those of you who have been following along, cores are actually not getting much faster. In fact, we're getting into a world of multi-core. We're already in the world of multi-core, really. And so, in fact, cores are getting a bit slower. And so if you've got a query engine that only runs on a single core and you want to make it faster, you've really got to look at ways of parallelizing those queries. And that's what the rest of this talk is really about. The other thing we did with the query engine inside Cortex is we made it kind of stateless, and we made it horizontally scalable. So if your queries are slow, just run more of them, is the idea. Except for it doesn't really work, right? So if you send us lots of very small queries, then we can parallelize them between different query engines. You know, we can scale up if you have a high concurrent query load. But everyone sitting here using Grafana, right, you load up and you maybe show 5 or 10 graphs on your dashboard. And if you're really aggressive, you might, you know, refresh them every few seconds. But that's still only going to be like single digits, maybe not even single digits QPS. And so parallelizing them is, you know, running multiple queries and then load balancing across those queries isn't really going to make it much faster. We've actually got to find a way of parallelizing individual queries. You can't really just keep scaling up the query and putting on bigger boxes with faster processors. They don't really exist anymore. So yeah, so this talk is really about how we handle big queries. Like if you come along and you ask to do a query over a few weeks worth of data, over a few million time series, how are we going to handle that? But before we get into that, first thing we did, like every good software engineer, we just went and put as much caching as possible into the system. So we went and we have a separate index in Cortex and a separate chunk store of storing the compressed time series data. And we just went and stuck memcaches in front of them. So the chunk store is easy because chunks are immutable. They don't change once they're written to disk. So you can just stick a memcache in, and when you write them, we do a write-through cache. So when you write them, they get written to memcache, which means you pretty much have like 90-something% hit rate on your chunk memcache. The index is a lot harder to cache because the index is always changing. And you're always adding new stuff to the index. And if you get the cache wrong, and we did have a bug that took us a long time to figure out where we turned out we got the caching wrong, you end up seeing gaps or missing data in your queries. So you've got to be really careful with caching kind of access to indexes like this. But anyway, it works now, and this made a big difference. This, like, now 80-90% of queries will just hit the index. We still have to process them on a single thread, but at least we're not putting load on the database, and we're not putting load on the chunk store. And we're effectively just saving that capacity for when someone does come along and run one of these really big queries. Anyway, now we actually get to the kind of exciting bit. Who here has heard of a project called Trickster by Comcast? Oh, not so many. OK, well, Trickster is this really cool thing that caches the results of the query. After you've executed the query, they basically take the result, they stick it in a cache, and then if you ask the same query twice, they return that result. So this is an awesome idea, right? This relieves even more pressure from the database and from the query execution. And we wanted to do this. Now, unfortunately, when we did this over a year ago now, the Trickster code wasn't very reusable, and there was a few things we didn't particularly like about it, and I didn't invent it, so I kind of wanted to write my own. I wanted to do it in a different style, I wanted to make it more reusable, and I wanted to do some more interesting things with it. So I built my own thing, we called it the query front end, and the query front end's job was to cache query results. We also used it as an opportunity to do a few more cool things. And I'm going to just deep dive into the query front end for 5 minutes and talk through what it does to process a request. So imagine you have a request, HTTP duration seconds count, right? And so we're rating it, we'll probably sum it. This is basically telling me the QPS of this shipping system. So the first thing we're going to do, we're going to take the query into the query front end, and we're going to align the steps. Right? What this means is, in the Prometheus world, you ask a query, say you ask it from the Prometheus UI, it's just going to say from right now, this second, this millisecond, back to, let's say, an hour ago, every 15 seconds, give me the value of this query. And that's how we plot the graph. And then you run it again, and it will say from right now, every 15 seconds, give me the value of this graph. And so those of you who have kind of seen this, you'll see, if your graphs are refreshing constantly, they're jumping around a little bit. They're not constant. Because if they're refreshing at a slightly different interval to the step, you're actually going to be getting back different data. So what we do here is we actually just align it so that the start of the graph, the start and end of the query, are multiples of the step. This stops the graph dancing around. It also makes the results much more predictable and therefore much more cacheable. This is a bit contentious, because when you ask Cortex a query, we're not actually returning you the answer to the query you asked. We're returning you the answer to a subtly different query. And there was a bit of back and forth when Trickster first came out. Trickster also does this. When Trickster first came out, there was a bit of back and forth over whether this was even a good thing. But what we did, because I work for Grafana Labs, we just changed Grafana to always issue step-aligned queries as well. So actually, if you're using Grafana on top of Prometheus and on top of Cortex, you won't notice any difference. It will behave exactly the same. And so if you're using Grafana to send queries to Cortex, this step alignment will be a no-op, right? It won't do anything. If you're doing it from your own user interface or you're doing it from a different user interface that doesn't do this step alignment, then Cortex will subtly adjust the query by a few seconds to make the result more cacheable. And this is where we start to diverge from what Trickster does. We start to do our own thing. We actually take that resulting query and we split it up. We split it up into different well, I can't use the term subqueries because they exist in Prometheus. Let's call them partial queries. We split them up into different partial queries. We chose in Cortex to split them up by day. This is a flag. You can configure this however you want. We're reusing this exact code base for a different system where we've chosen to split it up by hour instead of by day. But we chose to split it up by day, and this is because the index we use in Cortex is day-aligned. Every day you get a fresh index. So by splitting it up by day, we don't get any kind of read amplification onto the index. It's basically the same load. And now we've got 4 in this example, 4 independent queries. We can actually go and look them up in the cache. Sometimes you'll get a hit. You'll go like, oh, I executed this query a few days ago, and that day's results are already in the cache. Done. Don't need to do anything more. But actually what's more interesting is the, I don't know whether you can see my cursor, you can't. The one kind of towards the bottom on the right, there's kind of a partial hit. Like we looked in the cache for a day, we found it, but it didn't contain a whole 24 hours worth of data. It maybe only contained 20 hours or 18 hours worth of data. So in that case, we actually have to like construct a kind of a new partial query for the data that's missing. Then the final thing, it's not made obvious here, is we never cache. We never returned recent cached data. So it's configurable again. We set it to 10 minutes, but we will never use the cache for the last 10 minutes of data. You'll always go to the storage for 10 minutes of data. This is because Cortex is a push-based system. Prometheus pushes metrics to Cortex. It might get slightly behind. It might get behind by a minute or two. And so that last 10 minutes of data is still changing. It's still being updated. It's still not constant yet. Anyway, once we've constructed this list of queries, we've filtered out the ones that are already cached. We found the kind of partial cache hits. The partial cache hit logic is actually kind of fun because like you can have like an hour in the middle of a 24-hour block and then another like 30 minutes in the middle of that block, and you have to kind of decompose them into almost an arbitrary number of subqueries, which is kind of cool. Anyway, then we actually dispatch them in parallel off to our backend, right? And this is how we get the speed up. Because we're going to execute this one 4-day query, we're going to actually execute it as 3 separate queries, some with cached results. This is how we can start to parallelize, start to use that scale-out query service and actually process bits of this query in parallel. So there's a bit more to it in Cortex. There's a bit more we do. We actually have a queue that they go into first. This is because Cortex is a multi-tenant system. We have a few hundred clients sharing a Cortex cluster with isolated data. And we really don't want one client to come along and mash refresh on their browser and affect other clients' query performance. So we actually queue per client, and we do come a really naive, really basic quality of service between clients. Anyway, so that's how the query front end works. I wanted to talk about something that I thought was pretty cool. This idea came up about a month ago. Nothing we've done here is actually Cortex specific. So what happens if I wanted to use this system, use the query front end with a system that isn't Cortex? Could I use it with Thanos, let's say? Or could I just use it with Prometheus? It turns out you can. We did this PR, what's the date on here? 3rd of June, okay, so it's like 4 or 5 months ago. We did this PR to make it so that we can avoid that queuing logic and just dispatch the queries directly to any Prometheus-compatible API. So be it Thanos, be it Prometheus, even M3, even like Influx, anything that has a Prometheus-compatible API, you can now put the query front end in front of, and it will cache the results. So let's do a demo. This is about the only meme that actually works, by the way. The rest of them are just there for lols. So, okay, I'm just going to have to fiddle with my display a second. Mirror. So, window, screen. Right. So there's nothing up my sleeves. I do have make it a bit bigger. I do have a Grafana running in the background that I kind of set up beforehand, but there's nothing special there. what I'm going to do, I'm going to run the Cortex query front end. And it's just this, this one command here. Clear that up. There you go. So there's a pre-built config file that sets this up for you so you don't have to worry about it. And how many of you know about the demo.robustperception.io? This is like one of the most useful websites if you ever want to demo Prometheus to anyone. It's run by a small Irish startup run by one of the Prometheus maintainers. And he runs this and maintains this Prometheus, and it's got loads of data in it, and you can send it queries, and he doesn't mind me doing this. So I'm just going to use that as a demo. So I'm going to point the query front end at his Prometheus over the internet. There we go. Now I'm going to switch to the Grafana. Make that a bit bigger. Now I've got two data sources in here. I've got Prometheus pointed directly at robust perception, and I've got a cached version of Prometheus pointed at my local machine, which is then pointed at robust perception. So just to show this working, we'll go to the non-cached one first. And because I can never do histogram functions live, I'm just going to copy it out of the slides, paste that in. Now, this is only running over the last hour of data, so it takes 600 milliseconds, even though the server's running somewhere else in the world. So this is really quick, but we need to come up with something that's a bit more aggressive so you can really see the caching effect and the parallelism effect. So let's do a bit longer. If we do 3 hours, now it's still pretty quick. This is all now in the page cache in that Linux VM. Still pretty quick at 6 hours. This is actually the problem when you're doing like query optimization work on Prometheus. Prometheus is pretty quick. So it's quite hard to actually notice any difference. So let's do a day. Nope, it's got faster. Let's do 7 days. Here we go. Now it's actually kind of have to do some work. 2.5 seconds. That is quite quick. The Wi-Fi here is probably faster than my hotel. Anyway, so doing this request directly against Prometheus took 2.5 seconds. Now what I'm going to do is do this request against the local query front end on my laptop. This is going to, there's no cache because I've just started it, so it's got a completely empty cache. This is going to split the request up into 7 requests and dispatch them in parallel, all to a single Prometheus instance. So if I do that, you'll see it takes 1.4 seconds. So this is already faster. This is no caching. This is twice as fast, even though there's no cache, just through the parallelism effect. Interestingly, Gotham, one of the Prometheus maintainers, had a bet with me that this wouldn't be any faster, because it's still going to a single machine. But what this is really showing you is, even just by dispatching multiple independent queries to the same Prometheus node, it can start to use more of its cores. Each of those queries being processed on a single core, it can start to use the multi-cores on the box, and it gets faster. But then the really cool stuff happens. Now that I've run that query once, the results of this query are sitting in the cache on my local machine. And so if I refresh this, it takes 200 milliseconds. This is now 10 times faster than it was directly hitting the Prometheus. So, you know, I think that's pretty cool. So let's continue. Yes, great Odin's Raven. But that's not the end. This is where I finished the talk when I last gave it. I kind of stopped there, told people, you know, go and deploy this. It's one command. You go and deploy it inside your company and stick it between the Grafana and the Prometheus. You'll just relieve a load of load off of the Prometheus. All your users will be happy because their Grafana dashboards will be much faster, and we're done, right? Wrong. There's one more thing. This still means if you're executing a query for the last sub 24 hours worth of data, if you're executing a query for the last few hours worth of data, and you're hitting millions, tens of millions of time series, it's still not going to be fast enough. You know, internally, we really want queries to be instant. Like anything around the 100 millisecond mark is considered to be basically instant. And so our aim is to be able to process kind of millions, tens of millions of series in the hundreds of milliseconds. This is crazy, right? Because if you do the maths, I don't know, you're going to be pulling in gigabytes, if not tens of gigabytes of data in sub-second and aggregating it all together. Like, this is really hard. And this approach I've got, which I kind of call time-based parallelism, this isn't going to help in that approach. So we need a different form of parallelism, right? We need a different way of sharding the query, executing it across multiple cores, and combining the results. So for the sake of the rest of this talk, there's only 5 more minutes to go. For the sake of the rest of this talk, imagine all Prometheus queries look like this. And this actually isn't too much of a stretch. Like, this pattern probably covers 80% of queries to your Prometheus server. And the intuition there is that if I've got 10 million series in my query, I can't display 10 million series in a graph on Grafana. Like, there's just not that many pixels on my screen, right? So I'm having to do some form of aggregation. You know, there's a bunch of different forms of aggregation, but let's imagine sum is the way I'm reducing the cardinality of the results set so that I can display it to my users. And if my queries look like this, and you probably already know where I'm going, I can actually turn them into kind of almost an arbitrary number of partial queries over the different independent subsets of the data, execute these partial queries in parallel, and then re-aggregate the result to get the final result. And this is like, if anyone's paying attention at this point, this is just MapReduce, right? This is just the same theory behind MapReduce. These sums are independent. They can be executed independently. As long as each of these partial queries runs over independent data, then this is kind of accurate. I quoted the plus here because you're not actually adding these together. You need some kind of merge, reduce operation. And of course, like this shard equals 1 won't work either. Like Prometheus doesn't support this out the box. So this has to rely on some specific ways in which we lay the index out in Cortex. In Cortex, we hash every single time series and then mod 16 it. And that tells us the shard of the index we put it in. And we chose 16 just because we did this for a completely unrelated reason. We just wanted to shorten the row lengths in the index because we're overloading our big tables. But it enabled this extra thing. And again, by picking and aligning the sharding that you do at the very front end with the way we've laid out our index, we managed to do this without any amplification of the read load on the index. Anyway, we started doing this. Actually, I didn't start doing this. Owen, who is not in the audience, no? Owen and Cyril have kind of been working on this. And so I can't take the credit. But just to give you an example, this works. There's code, there's a PR that exists. And we're still we haven't got it into production yet, but it works. And to give you an example, here's a query over quite a few time series. This is running one of our larger clusters, and there's thousands of containers, and I think each machine has like 16 cores. So this is not millions, but this is hundreds of thousands of time series. Because it's we turn the caching off. We just want to highlight the effect of the parallelization. This query is artificially slow, but it really demonstrates the effect. So without the caching and without the parallelization, this query was taking about 10 seconds in our dev environment. And then once we turned the caching and parallelization on, the exact same query on the exact same data was about 3 times faster. So we were hoping it would be 16 times faster, but we'll take 3. Combined with everything else, I think that's a pretty big improvement. And once you turn caching on, once you deploy this in an environment with enough resources and hundreds of replicas of the query service, this actually gets significantly faster. Yeah, so I think that's amazing. And just to prove it's really doing that, this is a Jaeger trace of the query, and you can see that it's actually processing each partial query in parallel, which is super cool. We haven't done this yet, but we want to take this technology and apply it to Thanos. Right? In a Thanos environment, you can actually guarantee certain sets of data are isolated because they're stored at the edges in the individual Promethei. So, once we start merging this with some of the Thanos work, we can actually hopefully push down these partial aggregations out to the edges and only ship back, some pre-aggregated data and do the re-aggregation centrally. And hopefully, I think with something like Thanos, I think it's going to make even bigger difference than it makes with Cortex. So what are we going to do in the future? Well, we've kind of, I don't know whether you've realized, what we've kind of built is a query planner for PromQL. Like if anyone's here is familiar with SQL databases, we're really kind of looking at the query, we're picking it apart, we're figuring out which bits can be executed in parallel. And so we really want to kind of tease this apart a bit more and separate kind of the planning from the execution of the queries so that we can do even more interesting optimizations. One of the things I really want to do is, averages can't be re-aggregated, right? You get a different answer if you do that. But if you decompose an average into a sum divided by a count, you can parallelize the individual sum and count, do the binary operation centrally, and different tricks like this, I think, will make even more different Prometheus queries parallelizable and faster. And then this is one we've been talking about. I don't quite know whether this is actually going to work yet. We haven't done the work, but one of the weak points with Prometheus is if you do you want a year's worth of data, and you want to do like rate 30 days, over, get a rolling 1 month window over a year's worth of data, every single point is going to have to consider a whole month's worth of data, and this gets really expensive. So we want to kind of decompose a 30-day rate into like a series of 1-day rates. And then combining this with like maybe memorizing the cache or something, hopefully reuse overlapping 1-day rates. I think this is going to be really cool, and this is where we're going to take this, I hope. Anyway, the last and the most obvious, this is probably not the first time you're going to see this meme today. Yeah, anyone have any questions? Thank you very much. Yeah, I'm not going to do any product pitches, but if you do want them, we have a booth in the other room, and they'll give you them there. Go on. How do we even start to identify which queries are running slow? It's a good question. In production, we log every single query out to Loki, actually, funnily enough. And then we've built some scripts that process those logs, link them to traces, and we can just kind of literally look over the last few weeks' worth of queries, get the ones that were in that 1% that were slowest, and then go and view the traces for them. But this is kind of custom tooling we've built internally. I said I wasn't going to do any product pitches, but if you go to the booth, we're actually showing how we're trying to make a lot of that kind of, those tools we've developed, like more generic and more reusable for other people. So you can actually, in Grafana now, links directly from a log to a trace. But we do it just with logs. There's also an option on the query front end now we log every query because we've got a logging infrastructure. But if you don't have that, or if you don't want to log that much volume, you can tell the query front end only to log queries over a certain amount of time. I would log slow queries. And yeah, that's basically, we do log analysis to identify slow queries. Over there. Yeah, yeah. Yeah, so the question was, the thesis is we're repeating queries that overlap over existing data. But in a production environment, those windows are moving. So is there really that benefit? I mean, it depends what you do, right? I think it's pretty typical to set your Grafana to look over the last hour or maybe the last 3 hours worth of data. And if you're going back to that repeatedly, then yes, you're going to have quite a strong cache hit rate. Because, yeah, you're going to you might set, we have our Grafana set for a 10-second refresh period. So even if you've got the window open for a few minutes, you've probably issued, 20 queries for each panel, and you're going to have a huge hit rate just in the moment. But between different sessions, maybe not. Between different sessions, it depends how big your team is. It depends who's looking at these queries. One of the things, Grafana has its own inbuilt alerting system. I don't use it myself, but we use it internally at Grafana Labs, and that is just constantly doing the same query over and over again, like every few, tens of seconds or something. And when we introduced the caching system, that saw a huge increase in performance. That saw a huge cache hit rate. But it is workload dependent. Like, I think if you only ever go to your Grafana graphs, like, once a month, then no, there's not going to be any cache hit rate. Like, it's really for people who are using it more actively than that. Does that answer your question? Cool, yeah. How much time we got? Go on, quick follow-up. Yeah, I think it works. The intuition is it works. I just haven't sat down and done the math. Yeah, cool, definitely. Anyway, one more question. Yep. No, that's an interesting question, yeah. So the question was, we use Prometheus XOR chunks, which is like I've forgotten the name of the paper, really famous, the Gorilla paper, yeah. We basically use the Gorilla encoding in chunks for each individual time series in Prometheus and in Cortex and in Thanos. It's quite a popular system. We don't use the same format for the query results. We actually use protobufs. It's interesting that you mentioned that. I hadn't thought of it, because some of these query results are very large. We've had to configure our mem caches to store values of hundreds of megabytes of protobufs. And yeah, I see no reason why we couldn't encode them into the same XOR chunk format. Yeah, that makes a lot of sense. Even better, right, the XOR chunk format, when you have very, very repeatable timestamps, like with very even differences between them, gets really efficient. And in query results, you definitely have very even gaps between your values. I might actually go and look at doing that. I think that's a really good idea. Thank you. Go on then. We get this every time. Every time. So one of the Thanos maintainers is sitting just here, Bartek. Sorry, so the question was, I've mentioned Cortex and Thanos multiple times, and is there any plans to merge these projects? And categorically, I can say here, yes. No, I don't know. Like, that's like the Thanos was like, what? Bartek and I both live in London. We both enjoy going for a beer together. I think I would love to work more with him and more closely with him, making things like the query front end work with Thanos. We've actually recently embedded Thanos into Cortex. So Cortex can now store blocks in object stores in exactly the same way Thanos can. And this opens up more opportunities to collaborate on like extending Thanos performance for like the store gateway and stuff. I like the Thanos team. There's a large overlap with the Prometheus team and with the Cortex team, and I look forward to collaborating more. If that means the projects merge, great. If it doesn't, that's probably also fine. Yeah. They're very different deployment models, and that's not going to change, right? So, but no, good question. We get it every time. One more question. I think I've got time. I'm going to keep going until someone stops me, actually, at the back over there. We do as well. So, but we don't expose metrics for every individual query because the cardinality of that metric would be too high. But actually, if you look here, we probably, whilst running this, you see we've logged a slow query that took 1.4 seconds. So that's really the key for like things that can be used with like events and logs and things that can be used in metrics. Like if we put that query into a metric label, the cardinality of that metric would blow up really quickly. And then you'd need something like this to query it. But yeah. Oh, the question was, why don't I put we log slow queries, why don't we put it in a metric? And it's all about cardinality, yeah. Any more questions? No more? Am I missing anyone? Chris, go on. You had your hand moving. No? You were saying 2 minutes. Okay, cool. No more questions. Okay, one more, last one. Yeah. So, yeah. The question was, do we have like an explain on queries? Like we don't. We don't have at least a user accessible one. I don't think there's anything in Prometheus that does this either. I think it's a great idea. Like, as you said, we have Jaeger, so internally we can see why queries are slow because we just go and look at Jaeger. And I don't know whether we could expose that to customers because I don't know that there's no, like, well, there shouldn't be any interplay between different customers, and there shouldn't be any data in there that wouldn't be safe. But maybe that's the solution, would be to expose the trace, the Jaeger trace to the customers. So if they want to, they can go through it. And you can actually export Jaeger traces as big blobs of JSON, and then you could just, give an API for a customer to go and get that, and then they could load it into their own Jaeger instance and visualize it. Yeah, no, we don't have it, but I think it's a good idea, and especially when the query planner starts getting more and more complicated, and eventually we're going to have to deploy various different heuristics. We're already doing this for like deciding what to query in the index. There's basically no point in querying very, very large dimensions in the index. So we kind of already use some basic heuristics when we're hitting our inverted index to kind of figure out what to query. And yeah, like there's definitely feedback we could give to the user saying like, just don't bother touching this label. It's got 30 million entries in it. Doing regexes over that are never going to work. But no, it's a good idea. We don't do it, but I think we should. Right, I'm going to finish there. Thank you very much. Enjoy the rest of KubeCon.